Good morning.
Hi, Nick. How are you? Today is Veteran Day, so I do not intend to go for too long. Is that okay?
Yeah,
Yeah. Any question? Primary, we still go on for the homework first. Any question?
yeah, I was just wondering if you could kind of give like a brief overview of what we need to do in this week's programming assignment, because I was like watching the videos and I was still a little bit confused. I was just wondering if you could go over it.
Okay. Let's go over. So you have to let me know which part you're not sure. Okay. So let's go over the assignment. Okay. In the lecture, we can go over it later. So two quiz. Any question on this quiz?
No, I don't
No?
think so.
Okay, then program assignment 3. So program assignment 3, we do have this Scala manipulator. Okay, so the purpose for this one is to model it. Okay, let me click on this PDF file. So it is the same as your assignment. So here you are required to model this guy. So model this guy, you have the revolute join, number 1, number 2, and number 3, this one. If you want to make it revolute join, it's okay, but I do not require you to make this one a revolute join. You actually use the extender on here, it's good, okay? So some student, this one is also a revolute join, and some of student use the extender. I would say extender is okay. If you do revolute join plus extender, that's also okay. So if you look at these two join, it's almost like on a plane, right? On a plane. So it actually affecting only certain XY. So this guy affecting Z, right? Right? Because
Right.
this one is not moving. This part is not moving. So that's the goal is of this Scala arm. It's just like you have this one, the whole thing. This is on a plane. So if we use the baseball bat configuration, make it the longest one. L1 plus L2, then it will make a circle here, right? And then that's on the same plane, and then you will be able to go down on each one of here, okay? And if the length here and here, we say 1, 1, 1. Okay, I say that actually you just need to set the link to be 1, 1, 1. Okay, on this one, 1, 1, 1, 1 meter, 1 meter. That's so just pick it as simple as possible. So 1, 1, 1. And this one, initial condition, this one also extend for 1. So basically the workspace for this guy would be, the way you can work on for this guy would be, it'll be a cylinder. Okay, basically it's a cylinder because your baseball configuration will be reaching the whole thing. So anything inside here, the circle will be reachable, right? Because you can bend your arm, you can bend your arm to a certain location. So anything inside this circle will be reachable, and that one can go down, say, reach as far as 1 meter down. So it's a cylinder. Is okay. So that's
Yes.
a whole workspace you can work on. Okay, so in terms of workspace, you can describe something like that, and then you model this guy. Okay, that's one thing. So you actually come out kinetic diagram. So this one, I think you should be able to do it. Just choose the right XYZ on each one. So this one G is this direction, okay? Because your G, and then determine the X according to the 4 rules we talk about, right? So that actually should be fine. And then after that, this one, okay, this one is 1, 1, 0, 0, okay? This one I say it probably is wrong, okay? This one last time, the last lecture, I say a better one should be 0, 0, 1. It should be on Z, okay, not on X. Because you go down by 1. Go down by 1 means, okay, actually means that here, your initial condition is this guy go down by 1 meter is over here. That's your initial condition, because this one is on the Z direction, you go down by 1, right? So that's your initial condition. Your point is here. Now you need to actually find this location based on given theta 1, given theta 2, given extender D. Okay, and then from the frame 0, what should be the coordinate of this point, right? That's the whole goal, right? Is that okay?
Yeah. So I guess like another question I had
Mm?
is we need to use like a homogeneous transformation matrix for this.
Yes.
Okay.
Transformation metric, also orientation metric, yes.
Okay. Okay. Thank you.
Yeah, one by one. But you basically each joint you will have a transformation metric, a rotational metric, okay. And but also you need to consider the SYG change. So there is also one orientation metric need to be considered. Yes. Is that okay? Okay, this one is too simplified. This one don't some students just copy this one. That's not this one just for you to understand. It's really not a complete. It's 2D diagram. I actually prefer 3D one. But this third one is optional. I don't require everybody to have the third one as a regular join. Okay, this one is optional. You can just put a extender will be good enough. Oh, this one is optional. I don't deduct point if you actually miss that one. Is that okay so for this one so far?
Yeah, I think so.
The link length you can assume in displacement always 1, 1, 1, 1. Okay, whatever related to the length, that's assumed is always 1. Make it easier. Okay. Okay, now this one is this one called programming assignment 3. Okay. Next one is term project proposal. Okay. At the end of the course, I will require everybody to work on a term project. And with 3, I need you to write proposal. Okay. So to write proposal topic wise, any topic related to robot will be acceptable. I do not require you to do any specific part of the project. It's an open project. Okay, open project. But if you do want to have some direction, here are 3 possible kind of project. One is you can model a robot. If you don't have money to buy any robot, okay, then one thing is that you just follow whatever we have teach you to build a mathematical model for a robot. But well, don't just give me a one joint robot. Okay, that's actually too simple. I don't think that is a term project quality. Okay, so usually people would actually choose the 6 degree of freedom robot or 7 degree of freedom robot. Say 6 degree of freedom robot models or something like that. Okay, if you really want to do that, you can look at a lot of 6 degree of freedom robot and you try to model them. Okay, 1, 2, 3, 4, 5, 6, whatever type of 6 degree of freedom robot. That's typical complexity we are looking for. If you do mathematical modeling for one of these, okay, is okay. So that's number one. If you don't have the budget or I mean, you just want to work on some modeling that is actually okay. Just give me the mathematical model of each C.1, A1, A2, D1, or whatever, and put them together and put into the mathematical model and try to calculate for it. So some of kinetic diagram will be something like this. That's acceptable, something like this, but please work on your own part, okay? Do not copy from internet or certain model that exists, okay? You see, a lot of people join this kind of the kinematic model, the diagram model, okay? So that's one possible project if you can work on if you choose to build a mathematical model and also write a Python program for it, okay? Second one, if you do have budget or if you are really interested in building a robot of your own, it's welcome you buy some robot or you get some robot, but I want you to build it from scratch. do not use a robot that you take from other courses or from other people and play around it. And that's not a project, right? That's actually not even a project. So I do not welcome someone just actually use other people's robot to control. And I really you assemble one and tell me what project you work on. Say this is too expensive, okay? So usually we suggest a couple of hundred one. That's probably okay. Just build it and try to. And you may need to program it a little bit. Okay, even the failure is okay. I do not need you to be completely successful, but you need to take the video or PowerPoint at the end for us. Okay. You can try to get something like this robot building kits or something. Okay, whatever these are, okay, as long as you know how to build it and try to present it. Okay, we do not require you to have any some. Well, at least there should be some technical merit. Okay, so the whole process is to make sure that you actually work on some project. Okay. So that's the second one I'm looking for. Okay, sorry, I lost my slides. Let me bring it up again. Oh, I'm sorry, it actually is in here, okay? So you can assemble a robot from scratch. I do not accept someone who actually just borrow a robot from someone else. Okay, then that's another purpose for education, right? So that's the second one. Third one, if you don't have budget, you do not buy a robot, you do not want to build you actually do not want to model a complicated math model. Okay, there's another way you can work on the project is you can create a creative idea project. So this one is modeling. This one, second one is assembly implementation. This one is vision idea. Okay, the third possible project is idea. So this one is like, okay, you need to come up with an idea for us. So what kind of, okay, the first one is that this first one you do mathematical model, this is a CUDA one, and somebody build the code to control it, to model it. Okay, and this one is not real robot, it actually is on the 3D Blender. Okay, and then second one is assemble one that is. Third one, you can come up with some brand new idea. So you must work on some idea that's not even existing. So say the robot vacuum cleaner, this one is not considered to be a new idea anymore. Okay, so something you can buy from Amazon, something you can buy from company will not be considered to be a brand new idea. I want you to be getting out of the box, thinking about something new. Is that okay? So third project is like that. You have to work on something like that, okay? And then after you have the idea, you try to model it. But this model is not just math. You actually draw down some diagram or picture, front view, back view, whatever view you can draw on to help us to visualize what this idea should be, okay? And then you try to use Python or some other tool to help people to understand the project. Okay, try to understand the project. But the idea must be brand new. We welcome you to come out with brand new and no need to build a robot. Okay, this one just try to present your idea. And then these are the possible project topic. And then the proposal portion, the key point for proposal portion is that you should have a write-up, say some Google Doc file or some Word file, okay, some PDF file at least. This proposal is you need to write up your proposal, and inside the proposal you are trying to convince your manager they should fund your project. So this is the purpose of proposal. So you should cover your project idea and the title, what you are going to deliver, what will be the tool and material you want to do. Okay, and what's the key technical difficulty you need to overcome, and then your schedule. So these are the typical proposal content. Okay, you need to cover these different ones, but do not just write one sentence saying, okay, I'm going to build a Lego robot. Okay, that's not a proposal. Okay, now they cannot see what kind of project you want to work on. Okay, must have more detailed description of what tool you want to have, and what material you need, and your schedule. Okay, and then final report. This one is in the week 8 when you finish. We not only need you to write a report, but also need you to do presentation. Presentation, I accept PowerPoint, Google Slides, or YouTube link. You send me the video link is enough. Do not send me the MP4, MP3. Okay, that's actually too big. I do not need that. Okay, I do not need that. I do need this, and then send me the technical file too. When you implement the project. Okay, I will need these things. A write-up, a presentation, and a technical file. Okay, a set of technical files. So these are the, but this is in the VA. Now, if your proposal and the final report have different topic, that actually is acceptable. Okay, I'm okay. Like in the middle of the process, you decided that you are going to change topic. That is okay. Okay, so the proposal and the final report will be graded separately. Okay, totally separately. I won't look back to, I mean, your proposal to see how much you accomplish, the things that you promise. Okay, we do not do that. Okay, so it will be treated separately. First one, I just treat it as a proposal, see how much idea you generate, and also what kind of proposal you have created. Is that really feasible or not? That's what we look at for proposal. Okay, feasibility study. Okay, and the final report, we will look at the result you have. So this one, you need to have a full report on the project you have. And if the topic are different, that's okay. That's actually acceptable. Okay, and yeah, and the project will be graded based on this different point. Any questions so far?
I don't think so.
Okay, and what else you want to know? These are the 10 project and programming assignment 3. Any other question?
I do not think so.
Okay, no other question. So then I briefly go over the inverse kinematic. Okay, and then we are going to finish today. So lecture 6, we have inverse. So previous one, we go over Dennedy-Hardenberg metric. Okay, so far they are forward kinematic. Okay, forward kinematic. Forward kinematic means what? Means you do have a robot. You do have a robot. Okay, you do have some robot. And you do have some variable theta1, theta2, and then d1, d2, okay, whatever number you have. So you have a forward kinematic function. You put in your theta1, theta2, theta3, okay, and then your d1, d2, d3, and you will generate your XYZ location. Okay, this is called forward kinematic. Now, inverse kinematic means that, okay, we do have the desired XYZ. Okay, expected XYZ, and then I need to come out with what theta1, theta2, d1, d2 need to be. So go back to find your joint variables value from the coordinate to solve the equation to get your joint variables. Okay, so the forward kinematic is that you try to control your joint variable, and you get to some XYZ. Okay, and inverse kinematic is that you do want to drive a car to a certain location or at a certain speed. How can you find the required joint variable that would guide your robot arm to that location? Is that okay? That's the main idea of inverse kinematic. Okay, that's the main idea of the inverse kinematic. So this portion, okay, this portion, let's look at the slides. We do have forward kinematic. We model it with theta 1, theta 2, A1, A2, A3, A4, the different link lengths and the theta. Okay, and then we try to find the position for the end effector. Okay, the XYZ of the end effector. Okay, so this one is called forward kinematic, from joint variable to find end effector position or orientation. Inverse kinematic, on the other hand, is that I do know about where I want to go to. Then how can I go to? That's the problem I would need to solve. So from the XYZ, I go back to solve my theta 1, theta 2, A1, A2, A3, A4. Okay, these are fixed, but only using the theta 1, theta 2 to guide my robot to the right location. Okay, this is from end effector position and orientation to find your joint variables. Okay, this is inverse kinematic. So here we do need to have a model. So we actually write down this model like this. Okay, and then there is a inverse kinematic you need to solve. So here we do come out with the H1, H2. Okay, so we do get these. Okay, and then if you want to solve the problem, you need to use the XYZ time the big matrix and then solve theta 1, theta 2. That is killing. Okay, that actually take a lot of time to solve it. Okay, and but eventually you are solving some equation like this. Well, but usually that is actually very difficult. Okay, it actually solving a system of equation with trigonometry functions. That's not a simple task to do. Okay, it's a nonlinear equation. It's a nonlinear system of equation, and then numerical solution is possible, but symbolic reduction or symbolic solution is almost impossible. Okay. So this one, usually if people need a numerical solution possible, okay, you just try to do convergence analysis, try to approach the right theta 1, theta 2, fit the right theta 1, theta 2 to some equation. That's really possible, okay. But symbolic solution to find a closed form for the theta, the problem is too hard, okay, really too hard sometimes. So basically, inverse kinematic problem is you do have from the X to Q. Okay, so possibility to find a closed form solution, okay, is possible, but very difficult. Okay, and existing the multiple solution, yes. One location you may have 2 different or 3 different way to tune your robot. So for example, plenary robot. Okay, so this one does assume that there are two joints, so you can bend this way to get to the point here, but you can also bend your robot arm this way to the same point. So multiple solution of the different theta 1, theta 2 may exist. Okay, so trying to find the closed form actually take a long time and may not be necessary. Okay. So to solve the problem, you can use an algebraic intuition, geometry intuition way to solve the problem. Okay, and usually closed form is harder to do. Okay, but if you need to solve the problem, usually we want you to just go algebraic way or geometrical analysis way to solve it, okay? So you can set up your equation for the different theta and then your location of AYG, okay? You can set up that, and then you do try to solve it, okay, using your knowledgeable algebraic solution, okay, and then geometrical solution, try to solve it. Okay, so this one take a long time to solve to a certain format. Okay. Okay, let's see. This actually now this one go too far. Okay, too difficult. You need to have another math. Let's look at the easier version to as an example to show you a easier way to do it. Okay. So let's see. Inverse kinematic. Okay, here. Okay, let's jump to the graphical method. Okay, so one way that you can solve it inverse kinematic is if you do not use the system or equation solver, then you can use a graphical method. Okay, graphical method inverse kinematic problem in which we know a position and want any vector to go to. Then we need to find a joint variable. Okay. And then one way to do it is graphical approach. Okay, graphical approach, let's think about this one. It's actually a cylindrical manipulator, 2 degrees of freedom one. So here there's a river joint, there's extender. Okay, so that's assume that this one comes with the link length of A1, A2, A3, that is. And this one has an extender displacement D here. Okay, and a theta here, okay? And this one, if we actually look at the top view, okay, top view, the Z direction, let's look at the Z direction. Z direction, because it's actually fixed as the A1. And there's no extender in this direction, no extender in this direction, no extender in this direction. So basically, Z is fixed. G is fixed at the A1. Okay, so that part you don't need to worry. So now to look at the top view. Top view, you will have only XY. Okay, so you do know about your XYZ, we don't care. And then now you use the whatever XY given, you want to solve your theta. Theta is the amount you will rotate and the extender D. Okay, these are the number you want to have. So basically, okay, you know about your XY, you want to solve this D extender length, and this is theta. Okay, let's look at it. So total robot arm length from here to here, okay, will be A2 plus A3. Let's assume that that's actually R, a value of R. So this is R. R plus D is the total length here. Okay, that's the total length here. So R plus D times cosine theta. So that actually is your X. R plus D times sine theta. That's actually this Y portion. Okay. So you set up the equation. You do know about R plus D and R plus D theta. You have XY. Okay. So your Y over X is tangent theta. Okay, so y over x is tangent theta, so you can solve the theta now. So this is theta is arctangent T, okay, arctangent T, so theta is solved. Theta is solved, this one is solved, this one is solved. Then can you solve the R and solve your D? Okay, that's actually possible, right? Because you already have a theta. And your R is A2 plus A3. So your D actually is solvable. So your D will be, okay. So your tangent theta is 1T and square root this one. Okay, so your sine theta will be T over square root 1 plus T squared. Even T is the Y over X. So you come out with your sine theta. Okay, and your sine theta is R plus D over Y. Okay, with this one, your y, put it over here. So y sine theta, okay, minus r will be your t, your d, okay. And using this one, you should be able to sub your d as well, okay. Xy is known value. A2, A3 are known value as well, okay. And theta is sub by y over x. So theta is sub here, d is sub here. So you'll be able to figure out what would be the joint variable here and extenders joint variable here. Is that okay so far?
I think so.
This is a simple case for graphical method. So instead of solving the system of equation, graphic method is a way that you can help you. Okay, so that's one way you can do. And second one, let's look at this one. Go 2 degree of freedom manipulator. Okay, so here it is. This one actually there's an extender, and then there's a revolute joint. Okay, this one is the reverse order of this one. Okay, and let's see. Your z direction again is actually fixed length over here. Okay, z direction is fixed length over here. So right now you actually model, if you look at the top view again, okay, top view again, you get this. Okay, you have an extended d, and then the theta rotation over here, and you have A1, A3 over here. A2 is the g length of the g. Okay, and given these things, what you have the xy over here. Okay, so your x is really this much. Your y is this one. Okay, your y is this one. So your y should be what? Should be equal to your y over a3 should be your sine theta. Okay. I'm sorry. Yeah, I'm sorry. This one, actually, let's assume here my symbol. Okay, let me follow my symbol. So here, I do not call it y, I call it x. Okay, I call this section as x, but it should be your y value. Okay, so anyway, let's just call this one x. So this is x. So your x over your a3 would be your sine theta. Okay, and your r, this r is from here to here. Okay, this one is a3. Okay, your r is actually this. Okay, is this. Okay, so your z, let's assume z is this portion. So z plus d, okay, minus this one is your r. Okay, this whole thing is your y, this value. Let's assume this is some given value. Okay. Okay, I'm sorry. This is g actually is a total value from here to here. Okay, the length from here to here. So g minus this portion r minus this portion minus a1. Okay, you will get your d. Okay, so that's the way you calculate it. Okay, the portion is r. R is calculated by this. If this one is x, go from here to here. So this is square root of a3 squared minus x is this length here. Your total length from here to here is actually g. Okay, so you minus that one, minus your d, minus your a1, you get your d. So your d can be sub even this one. So g is something you know. What x is something you know. A1, A3 is also something you know. So you sub the d. Okay. And you can also sub the theta using the x over a3. Okay, so then your d, theta and d are subbed. Okay. Okay, example number 3, if you do have this second 2 degree of freedom 1, you have two revolute join, okay? Your G at this moment would be A1 plus A3. And then if you look at the top view, it's a plenary rotator, two rotator revolute joints, okay? And you are given a certain SY location here. Okay, let's assume that here you do have this S and Y. R is solvable because it's S squared plus Y squared. So R is also known, this is known, this is known, okay? And then your theta 1 is this rotator here, theta 2 is this rotator here. So theta 1 is actually this phi 1 minus phi 2 minus phi 1. So phi 2 is this one. Phi 1 is this one. Okay. So theta 1 is like that. Theta 2 is 180 degree minus this phi 3. Okay. It's a exterior angle. Okay. Exterior angle of this guy. So it's 180 degree minus the phi 3. Okay. So now phi 1 is actually a cosine of, so this is using cosine rule. You do have the A2, A4, 2 angle, and also have a three side to solve the theta 1. That's cosine rule. Okay, you get this one. And then theta 2, phi 2 is from here to here. You do have y and x, so you actually can solve the phi 2. And phi 2 minus phi 1, you get your theta 1. So theta 1 it can be solved using this equation 3 and 4. Okay. And phi 3 is over here, is this angle. This angle, you also use the arccosine rule. Okay. You use the cosine rule to find the arccosine of it because you have the A2, A4, and R. You should be able to find this angle. And once you solve this angle, that's a phi 3, and your theta 2 is 180 degree minus the phi 3. Is that okay?
I think so.
So the whole thing is graphical method is you need to set up your graphical model first. You need to set up your graphical model first. Okay. And then assigning the variable and try to solve the missing variables. And that will help you to find your inverse kinematic. Okay. So these are the easier 2, 3 degree of freedom one. And the textbook portion, I think that's way harder, okay? So there are things, more inside equation you can do, how to study higher degree of freedom one, okay? And usually this one, we divide it into two parts, lobar arm and lobar wrist, 2, 3 section, and then solve it one by one. Is that okay? If it's more than 3 degree of freedom, you don't want to make it too complicated. Just solve a certain section first. Is that okay? So, and then solve angle by angle, okay? And that require a lot of computation, okay? Okay, so those portion we suggest to study these different graphical method to solve it, okay? So there are several ways you can solve it. If you do have a good symbolic solver, like we do have the SIMP, okay? We do have a SIMP in Python. If you know how to do it, how to solve it in using the nonlinear equation, you can try it, okay? If you cannot solve it or cannot find a closed form, then you try to use the numerical method to solve it. And another way to do it is you don't rely on the system of equation. You're actually using the graphical method and use graphical method to find your joint variables. Okay? Okay, these are, I just go over the guideline. Any questions so far?
I do not think so right now.
Okay, so today I'm up to here, okay? And wish you have a happy Veteran Day, okay? You serve in the armed force before?
No, I did not, but I have a few
Oh,
friends
you
who
don't.
are currently serving.
Okay. When I was young, I grew up in Taiwan, and I do go into the military service as a naval officer. I'm served in some submarine ship and some destroyer before as a weaponry officer. And South China Sea is usually have a lot of trouble, right? So we do travel to. I mean, we do have some trip to those region. It's a fun to serve in the military. Okay, I'm in charge of the closing combat system. All of the Taiwanese naval ships are made by U.S., right? So almost the same maintenance system, same weaponry system. And a lot of them say the closing combat system, those metric guns, they are also robot. In some way, they are also robot. You see the closing combat system
No, I have not.
or torpedo? Okay, that's actually when the ship is getting to the so-called missile or some airplane is getting too close. No, not this one. Okay, actually, I should use the close. This okay. You see this before in picture? Okay.
Yeah, I think I have.
Yeah, it will shoot. These are fast guns, and they can shoot almost 360 degree. And then it's what when enemy's airplane is coming close. So you do have a ship, and usually you put this kind of combat system at the front and somewhere after your main gun. Okay, you have the closing combat system. So when some airplane fly by or some missile fly by to attack your ship, right? You would use the radar to check it and then shoot back. So it also is a robot system, sense and react, sense and react. Is that okay?
Yeah.
Yeah. So that's also one of the robot application. Okay, and some of the closing combat system even installed on cars, on a lot of system. Okay, and you hear of the what the Israel's Iron Dome system. Have you heard of this one?
Oh, yeah, I have heard of that. Yeah.
Yeah, this one similar. Okay, this one is instead of shooting fast gun, they're shooting the low cost rocket to shoot down the enemy rockets. Okay, it's an air defense system. Okay. Okay, that's what my experience when I served in the Navy. Okay, when I served in the Navy, so I'm in charge of the weaponry system. Okay. Okay. See you next time. Okay. Bye bye.
Bye.
Bye bye.
Thank you for your service. Yeah.
Yeah. Thank you. Bye bye.